Lab 1, constant velocity. So the purpose of the lab was to find and create an example of constant velocity and explain the mechanics behind it. The relevant physical principle was Newton's second law, which is defined here. Since the mass of the observed system was constant, we could just use net force equals mass times acceleration from Newton's second law, which implies that if acceleration is 0, force is also 0. The other important formula for this was position update formula, because that's the linear model for the graphs, and it's where tracker will pool the average velocity for the system. The results of this experiment will show that situational velocity is constant acceleration and the force acting on the system are both zero. For the design, the system for showing constant velocity was this stress wad right here, because the shape made it easy to roll and easy to roll in a straight line. The additional equipment was a 30 centimeter or 12-inch ruler as a reference for tracker to keep the system rolling straight. The system was a stress wad. The surroundings were the ruler, the desk, and the air. The initial conditions for the experiment are in the picture on the left. The wad starts not moving, and since the coordinate system for tracker had 0, 0 at this top left corner of the ruler, the center of the wad that I was tracking position from is actually behind the y-axis. So the wad starts in the negative x position. I simply tapped the wad and observed the movement in tracker. Data for tracker is on the right. The orange line is the observed line of best fit for position versus time. The most important pieces of data are this A parameter. This value is 25.4 centimeters and reports as 2.54 decimeters because I didn't calibrate it. And other important pieces of information are in row 41, the tracker lasted for 1.368 seconds, and the final position of the system was plus 34.11 centimeters tracker. Now, I tried to make this line up in code. The system's initial position vector was negative about half a centimeter, which I tried to mirror in the ideal version, but couldn't make it work. For the ideal version, I simply assumed that the system was moving at a constant velocity the whole way through, so that means that initial position here equals final position. I simply pulled the velocity it was moving at from tracker, so that would be 25.4 centimeters a second. And delta t is the about how well I can estimate a frame rate. It lasts for 1.368 seconds, and this position vector here is how many centimeters that this system would ideally cover in a frame, which is about 0.8 centimeters. So in the ideal model, you can see velocity versus time is a flat line, which is good because that means acceleration is 0. But in the position versus time, as you can see, I did not get initial position to be negative at the start. The models together and the assumptions, blue line is the observed position, orange line is the predicted position. They do end at the same place, plus 34.11 centimeters. All right. The assumptions to get this to happen, that the observed system did move at a constant velocity. It didn't because there was a jerk, because it started the experiment not moving. It also means the position, air resistance, and the force exerted on the observed system by the rule are all negligible because we don't deal with that in ideal, and the points on the observed system and the predicted system are assumed to occur at the same time, so they could be cleanly compared. In reality, they didn't exactly line up, which is an error source. One point on the ideal model had to be estimated from the jerk, which made it nonsensical, which is another error source. The observed system receives force on the z-axis in reality, which could not be properly accounted for, and tracker relies on human input, which means that the position is naturally going to be off in reality. So for the discussions, to sum up these two answers, for what if the x-axis is inverted, all mathematical calculations will invert, while all force vectors will not, because force vectors are not dependent on a superimposed coordinate system. Mathematical calculations are. For what does it mean? In the cases I observed, I can see how many forces roughly are involved because I designed the experiment, and Newton's third law says that everything has an equal and opposite reaction. They are all listed in this block. So conclusions: velocity is constant when that force is 0.